Good afternoon and welcome to week 3 for S2S monthly webinar. Today we have two speakers including Taylor Grace and Dr. Dylan Amaya. Taylor is from University of Oklahoma and Dylan works at NOAA PSL. So please refer to the week 3 for website posted in the chat box, and please also use the discussion document in the chat box during and even after the webinar. The speakers will contribute to it in order to address any questions from you to foster relaxed atmosphere of the week 3 for S2S webinar. The speakers will contribute to it in order to the end. Our next webinar will be on May 6th at 2 p.m. Eastern Daylight Time. Again, thank you to the speakers, and let's head start with Taylor.
Okay, perfect. Thank you for the introduction. So again, my name is Taylor Grace. I am a PhD candidate at the University of Oklahoma. And today I will be speaking about winter warm spell events and really a case study on a winter warm spell event that happened in the Southern Great Plains in 2021. And so this is a work that I just recently submitted for publication by a few colleagues of mine, and we hope to kind of hear back soon. So to kind of talk a bit about motivation of this work, so heat waves specifically within the summer season are known to really foster a lot of impacts on socio and economic sectors. One in particular is human health, and a really great example that's been heavily studied is in the Pacific Northwest 2021 heat wave event that recently happened. And an example here is kind of to give you an idea of how extreme those temperatures were during this event. The bottom left figure shows the 2-meter temperature anomaly across much of the North America, and you can kind of see in the Pacific Northwest how extreme those anomalies reach close to 15, if not greater than 15 degrees Celsius. And then on the bottom right figure is a time series across that event that shows the number of emergency visits due to heat-related illnesses. And really the key line to focus on this figure is the black solid line, which shows a strong peak kind of towards the end of June, which is very different than the other lines, which are kind of the climatology or different events that had happened. So obviously this event is pretty well studied with respect to human health, but it was also studied with respect to agriculture. So the effect that these extreme temperatures had on crop yields during that time is kind of shown in this bottom right figure. So just to kind of give a brief overview, the y-axis is really the crop vegetation index in different regions across the Pacific Northwest into Canada as well. And so the shaded vertical gray lines in this study is kind of the time period of this Pacific Northwest 2021 heat wave event. And really what you can see is through a lot of the regions, there was a sharp decline in the vegetation index either during the event or shortly after the event. So not only does extreme heat in the summer season have large impacts on human health, agriculture, but also on water resources and the energy sector. And so how does this kind of relate to the impacts that are seen during winter warm spell events or extreme heat during the winter season is kind of something that was brought to our attention through the USDA with the focus of pests. And so they had a large question on, we're seeing kind of pests stick around within croplands for a longer period of time. Maybe why is this occurring? Is this due to the increase in frequency of these, warmer temperatures during the winter season, which has been studied in previous studies. So this figure here on this slide really shows different ways that insects and pests are able to really populate more, change geographical regions, further spread diseases due to plants due to the ability to remain alive during a primal point for some specific crops, specifically winter wheat for the Southern Great Plains. And so that's kind of a big motivation for looking at these winter warm spell events during within the Southern Great Plains is that winter wheat is a really dominant crop and a really important crop for the Southern Great Plains. And there is this really important point within the growth stage of winter wheat for temperatures to kind of dip below freezing and provide that frost point. And sometimes if the winter wheat crop isn't able to experience that, then it actually can, in and of itself, cause a loss in crop yield, as well as, again, these pests can kind of stick around and farmers aren't able to properly mitigate of these pests before they're able to kind of get to the crops and really lower the amount of yield from a specific planting and harvesting. And so again, that's why we kind of wanted to focus on what's kind of going on, what are maybe some of the characteristics that are at play during a winter warm spell event within the Southern Great Plains, and really are these increasing in frequency. And so just to kind of give a base overview of kind of drivers and different characteristics that we wanted to look at for this study. So again, atmospheric blocking is really a main driver for heat wave events. The top right figure shows an example of that. Specifically, a lot of these case studies that have been done previously really shown that this atmospheric blocking pattern is mostly set up over the impacted region. So again, as I think a lot of us are aware, when you have this atmospheric blocking high, you get increased subsidence towards the surface, which then increases the adiabatic warming at the surface. And through kind of the next characteristic that we wanted to look at, through land atmospheric interaction feedbacks, you can really supplement this extreme heat that may already be in place due to synoptic sail driving. And so the bottom figure on the right is really showing kind of this connection between drought and heat waves, but really shows this land atmospheric interaction between a decrease in precipitation while you have an increase in temperature causes the land to kind of desiccate as evaporative demand is increased. And then further, as there's no replenishment of precipitation, you get this constant cycle of temperatures wanting to extract out available moisture when there isn't any available moisture at the surface, which then further causes sensible heat flux and latent heat flux at the surface to increase temperatures. And again, we have seen in previous studies that heat waves are predicted to increase in frequency, duration, and intensity across many regions globally, but specifically in kind of North America and kind of the eastern and southern portions of the US. And so again, how does this relate to maybe what trends are being seen during the winter season of extreme heat? A study done by Brown et al. In 2008 found a positive trend in the location parameter of daily maximum temperatures within North America, specifically during the boreal winter season. And so this location parameter is the center of the distribution. So we're seeing this shift in a positive trend of the center of the distribution towards these warmer temperatures, specifically during the winter season. So again, this kind of raises a question, are we seeing an increase in these winter warm spell events? And for this study, specifically in the Southern Great Plains. And so that's what we found. So in this figure, I'll talk about a little bit about the classification of the winter warm spell events in the next slide. But what we found was that there has been an increasing trend in frequency of these winter warm spell events across the Southern Great Plains, really starting from kind of the mid 80s. And so we can see this gradual trend each kind of decade as we progress towards the future. So understanding maybe the characteristics that are associated with these extreme events, as well as understanding is their predictability, lead time with these events, is really of importance to mitigate a lot of the socioeconomic impacts. So again, really the key question for this study was to understand what atmospheric and surface characteristics were drivers of the extreme heat periods in the Southern Great Plains during December of 2021. And for those who are kind of unaware what kind of the temperatures were like within this region during this time, just to give a little bit of a fun factor reference, on Christmas of 2021 in Oklahoma, temperatures were 80 degrees and above. So degrees Fahrenheit and above. So that's pretty extreme, if you ask me. And so we kind of wanted to use this as a baseline to kind of stem through the rest of understanding all of these events. So just kind of quickly touching on the data and methods of the study. So we use the data set ERA 5 reanalysis at a 0.5 degree spatial resolution. Again, the study domain is outlined in that top right figure through the gray box, which is classified as the Southern Great Plains. We initially grabbed 3 hourly temperature and then further derived daily values from the raw data. All of the variables that were used within this study were linearly detrended and standardized. Again, we wanted to linearly detrend just because we want to remove already that warming that would be seen within the data and really just understand to the raw of it what's going on. And so in the table kind of below all of that is a list of all of the variables that were talked about within this study that I have submitted for review. But for the case of time, and for this presentation, the red box variables are the ones that I will focus on within this talk. And so again, really the topic of defining these extreme heat events is heavily debated. So this is kind of the classification that we landed on. So the first classification is there needed to be 3 or more consecutive days that had experienced a daily maximum 2-meter temperature anomaly greater than the 90th percentile. Again, using this relative threshold allows for the use of expanding this out through different regions. And we wanted to provide a 7-day running window to kind of cancel out a lot of the noise that can be seen on a daily basis when calculating percentiles. The second criteria is really understanding how to end these events, as that's not as heavily talked about within the field. So criteria 1 had to not be met for 4 or more consecutive days in order for the winter warm spell event to end. And really the reasoning behind this is this provides enough leeway that we can say that most of the events within one period that's within this classification are majority synoptically driven by the same thing. So if you don't provide enough leeway, you might get too choppy of events that may actually concatenate into one synoptically driven event. So allowing for 4 or more days really provides that synoptic independence. And so an example for this is outlined in the figure below. So the solid red line is the daily maximum standardized temperature anomalies. The dash red line is the 90th percentile. The kind of shaded gray regions show when the daily maximum temperature anomalies are above the 90th percentile. And what we can see is that even within this event, there were gap periods where the temperature anomaly wasn't above the 90th percentile, but due to our classification, the purple vertical lines denote the start and end period. So for this case, the start period would have been the 29th of November of 2021 through the 17th of December of 2021. And so again, we kind of employed this and generated a climatology from 1950 through 2021. And the 2021 events are outlined in the table below. And so specifically the first event, like I said, was from November 29th of 21 through December 17th of 2021. That lasted 22 days and had an average magnitude of 2-meter temperature anomalies at 5.25 degrees Celsius above normal. And so for the second event, even though it was shorter lived, only lasted about 10 days, the intensity of that event was actually much higher comparative to the first event. And that's something to kind of keep in mind as we progress through the rest of this presentation. So just to kind of give a background of really the pattern of the maximum and minimum temperature anomalies, from this point on, all of the figures and slides will be set up the same, just we'll have different variables. So if you split the screen down the middle, the left 6 subplot panels are really correspondent to the first winter warm spell event, while the right 6 panels are really correspondent to the second winter warm spell event. And so what we can see here is that specifically for the daily maximum 2-meter temperature anomalies, we see a strong uptick in significance of these temperature anomalies across much of the region through the very beginning and onset of the winter warm spell event number 1. We see it kind of persist in some regions throughout the rest of the first event and really maintain through the end of that first event. And then what can really be seen is, again, that intensity of the second event was much stronger. And so a lot of these anomalies during the second event reached upwards of 12 to greater degrees Celsius above normal, which is obviously not super common for this area. And so we further wanted to understand if there was really any relief provided during this case study overnight. This is really done a lot for human health perspectives of extreme heat, but we took it in the standpoint of kind of the land surface. So the land surface isn't able to kind of get a relief of this constant need of evaporation at the surface, then obviously that may cause the land to desiccate a lot quicker than normal. And so we wanted to look at what was the trend and pattern of daily minimum temperature anomalies. And really what was seen is that, yeah, they were above normal, but they didn't really get significantly above normal until the very end of the first winter warm spell event, and then throughout the duration of the second winter warm spell event. So we did have a case where, there was both very strong and above normal extreme daily maximum and minimum temperature anomalies, which is important to take into consideration when looking kind of at these land atmospheric interactions. So we first wanted to look at just the general pattern. What is, the Rossby wave pattern? What was that like during this event? So what we have plotted here are daily 500 hectopascal geopotential height anomalies. The shaded is the anomalies, and they are only shaded if they were significant. And then the dashed lines are the actual geopotential height values contoured there. And so what we can really see is that across much of the region, which is shown by that gray box across the US, there really weren't significantly above normal geopotential height anomalies at 500 hectopascals, which is a little bit shocking. For an event this extreme, one would probably expect there to be a really strong ridging pattern, specifically over the impacted region, which is not really what was shown. And so this kind of highlighted potentially one thing that might be either different or important within this work is that the atmospheric blocking high that I had talked about as a main driver of heatwave events really didn't set into place until really the beginning and prior to the second winter warm spell event. And so another big thing to note is that it was not co-located with the impacted region, but this atmospheric blocking pattern really set into place and maintained for several weeks and throughout the second winter warm spell event, which may help to explain potentially why some of the intensities of the second event, temperature anomaly wise, were a lot greater. And one big thing that we found with this kind of result here is that this blocking high feature is pretty similarly resonates with a specific winter weather regime that's been talked about in a prior study. So a study done by Millen et al. In 2022 really looked at kind of 4 to 5 classifications of winter weather regimes that dominate during the winter season. So one of the weather regimes is called an Alaskan ridge, which is really this ridge dominant over Alaska within a trough that extends throughout northern North America and through the west coast of the US, which is really kind of the pattern that we saw through this second winter warm spell event. So that was kind of one major finding with this work. Again, a lot of people, when you think about extreme temperatures, you think that there's probably some sort of extreme warm air temperature advection. So we wanted to kind of dive into that. And so really what we found here is that there weren't any significantly extreme warm air temperature advection throughout any of the periods through each winter warm spell event. And that was a little bit of a shock because we would have expected at least, a moderate warm air advection throughout the region as these temperatures did reach 12 degrees Celsius above normal. So this really just brought up a bit more concern of what's maybe going on at play closer to the surface. And that's kind of what I'll talk about here in a moment. And so before I do that, I really wanted to understand what the soil moisture was like throughout and after these events. And so one thing that we found was that there was kind of this divide, a diagonal divide between the southwest and the northeast portion of the domain, where portions kind of, southwest of Texas had above normal, soil moisture available, while towards the northeast of the Southern Great Plains domain, the soil moisture anomalies were below normal. But we didn't see a significant change in these soil moisture anomalies as we progressed through these events, which again brought up a little bit more question of potentially how strong were some of these interactions at the surface. So again, just to kind of keep in the back of your mind of that divide between above normal soil moisture to the southwest of the domain to below normal soil moisture to the northeast of the domain. And really what we can kind of see is during the first winter warm spell event that there's almost this divide in daily sensible heat flux at the surface, where regions that had below normal soil moisture had above normal sensible heat flux, which makes sense as that would be the driving and main kind of heat flux at the surface due to the lack of available moisture. And then one interesting thing that we saw is that during really the onset and the very beginning of the second winter warm spell period, much of the domain was dominated by daily sensible heat flux, which could just be due to having these events almost back to back to each other, really enhancing the amount of daily sensible heat flux at the surface due to kind of land desiccation from the first event. Then moving into daily latent heat flux, this one's a little bit messier in kind of what we saw. There isn't as clear as a divide, but there still is a little bit of that divide based upon where there was above normal soil moisture and below normal soil moisture. But really one thing to highlight here is throughout the first event, kind of in this middle period, there was a significant uptick in the daily latent heat flux, really across a little bit of this Red River region, so extending from really the western portion of Oklahoma through kind of that middle central portion of Texas. That's kind of something that really was highlighted. And then specifically, again, when we look into the second event, we do see more of that divide between the regions, southwest of this domain had, above normal soil moisture, so daily latent heat flux at the surface would be above normal. So again, all of these kind of match up. So based upon everything that we found in this study was a lot of moving parts. And so we wanted to find a way to kind of concatenate all these moving parts together. And so we kind of pieced together this schematic and just a couple things to quickly touch on. So one of the main factors is really the strengthening high and blocking high really west of the impacted region. So that was really one key finding. Obviously, the sensible heat flux and latent heat flux were a little bit offset from each other, depending upon the regions that had above normal soil moisture compared to below normal soil moisture. There really was weak warm air advection, so not as strong as what would be expected. But again, we kind of looked into more of these variables in our study and in the paper, which I would gladly share another time. So again, just to kind of discuss the key conclusions, that atmospheric blocking high, or in other words, Alaskan Ridge, was not co-located with the impacted region or the Southern Great Plains, which is a really, really key finding. There was really weak warm air advection across the region, which was not expected. Again, below normal soil moisture really enhanced that sensible heat flux near the surface, really across the northeast portion of the Southern Great Plains, while the opposite was seen specifically during the second winter warm spell event, where above normal soil moisture really supported latent heat flux across that southwestern portion of the Southern Great Plains. And lastly, just a little bit of future work. We're wanting to really investigate atmospheric drivers for all of these winter warm spell events in the Southern Great Plains, understand there's some similarities and differences between kind of these heat wave events during the summer and then the extreme heat or winter warm spell events during the winter. And again, kind of investigate teleconnections to these winter warm spell events, as there is some strong connections, teleconnections to changes in precipitation and temperature during the winter season, specifically for this kind of Southern Great Plains region. And with that, I'd be happy to take any questions and just acknowledge the NSF grant for supporting this work.
Thank you, Taylor. Yeah, it was a great talk and I quite enjoyed. So any questions from the audience? Yeah, I have a quick question. So I was quite interested with the two parts. One was from the Pacific Northwest, and also another one is in the Texas. But second of all, the Texas is quite huge, and then Western Texas and Eastern Texas it's quite different. So in Texas, is there any difference between East and West? I believe the Western Texas is under a dry climate, but Eastern is under a wet regime due to the Gulf of Mexico. So are there any indications from reanalysis or climate modeling research from your investigation?
Yeah, so I mean, we definitely, especially with the soil moisture, you can really see that there is that divide. But specifically, kind of with this, I think the lead up to this event was a bit important, as there was precipitation kind of coming off kind of more of that monsoon region,
Mm,
and was able to kind of provide precipitation to actually the western portion of Texas comparative to the eastern portion. And so I think, like I said, there's a lot of moving parts. So I think understanding everything that's at play, specifically with these winter warm spell events, is pretty different compared to what you would see during, the summer season, which is what you have talked about. You would expect during the summer season there to be a drier western
mhm.
Texas compared to the eastern Texas, and I'm not sure that's exactly what is seen during the winter warm spell events.
Okay. Yep. Thank you. Now, another question is that you are for the investigation, you are using only reanalysis or any kind of modeling setup?
Yeah, so for the time being, we just settled on reanalysis. We would like to
Mhm.
expand it a bit more to look at kind of how well did models pick up on this event. But specifically for this case, we did a preliminary on that, and models did do a pretty good job of picking up on this event and did provide predictability. I'm pretty sure at least a week out. And so we really are going to expand a bit more into observations to see if the reanalysis is matching what observations characteristics are kind of signaling.
Understood. Okay. Because our program, weather program office, we are anticipating like a week 3 for weather forecast, especially with, in the West, water in the West. We are quite concerned with it pressure from the Congress. So I think
Mhm.
your coming study will be very appreciated with that
Yeah,
regard. So thank you, Taylor. Okay,
yeah,
our next speaker. Yep. Yeah, our next speaker will be Dr. Dylan Amaya. So let me make him the presenter.